Welcome back to The Sleepy Scientist, where we explore the universe one yawn at a time. Tonight, we're going on a slow, soothing journey into one of the biggest questions there is. Where does space stop? It's a question that sounds simple, maybe even a little silly at first, but the deeper you fall into it, the more it stretches your mind, like the universe itself. As always, I hope this video helps you drift off gently, or at least helps you put your worries into perspective by zooming out a few billion light years. Of course, there's a small risk that it might be too interesting and keep you awake, but if that happens, well, at least you'll have learned something fascinating along the way. Before we float off into the stars together, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Stockholm at 11:30 p.m? Or listening from a couch in Melbourne at 3 in the afternoon while pretending to work? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like the cosmic background radiation. And as we begin this gentle voyage into the vast unknown, remember, this video is for educational and relaxation purposes only, and is not intended as medical advice or a substitute for professional treatment. Ready? Let's begin. What exactly is space? That silent black canvas we see when we look up at the stars. What is it really? For most of us, space is simply nothing. A void. A big, empty place where stars float, planets orbit, and socks mysteriously vanish. But space, as it turns out, is anything but empty. In fact, it's one of the most active, mysterious, and misunderstood parts of the universe. To begin with, let's go back to the basics. For centuries, people thought of space as a simple backdrop. Imagine a stage in a theatre. Space was the flat wooden floor, and planets and stars were the actors moving around on top of it. This idea came largely from Sir Isaac Newton, who believed that space was absolute, a fixed, unchanging arena in which everything happened. Time ticked along at the same pace for everyone, and space was just the three-dimensional grid that held it all. Then along came a fellow with wild hair and a tendency to scribble on chalkboards, Albert Einstein. He shattered that tidy image and replaced it with something far more strange and elegant. According to Einstein, space isn't a passive backdrop at all. It's a living, stretchy fabric, one that bends, twists, and warps in the presence of mass and energy. Together, space and time form a four-dimensional construct called space-time, and this dynamic stage actually responds to what's happening on it. To visualize this, picture a trampoline. Place a bowling ball in the center, and the fabric dips. Now roll a marble across the surface. Instead of going in a straight line, it curves around the dip. That's a bit like how gravity works in Einstein's universe. Massive objects like stars and planets bend the space-time around them, and that curvature is what we perceive as gravity. We don't fall toward Earth because it's pulling us like a magnet. We fall because Earth has warped space-time, and we're rolling into the dip. Now, you might be thinking, okay, fine, space bends. But when there's nothing in it, when we're in the gaps between stars, isn't that just nothing? Not quite. Even in the darkest, loneliest corners of the universe, space is still full of activity. Thanks to quantum mechanics, we now understand that empty space isn't truly empty at all. At the smallest scales imaginable, far smaller than atoms, space is buzzing with what physicists call quantum fields. These fields aren't things in space, they are space. Every particle in the universe arises from its corresponding field. An electron comes from the electron field, a photon from the electromagnetic field. And even when no particles are present, these fields are never completely still. They fluctuate constantly, producing tiny, momentary particles that appear and vanish like cosmic fireflies. This jittery energy in empty space is called vacuum energy. It's a bit like the surface of a pond. From far away it looks calm, but get up close and you'll see little ripples, disturbances, the occasional jumping fish. What seems smooth and featureless from a distance is actually full of hidden motion. This is why physicists say the vacuum is not empty. It seethes with potential. Particles pop in and out of existence in fleeting pairs, virtual particles as they're known. They can't be directly observed, but their effects can be measured. For example, they influence how electrons behave around atomic nuclei, and even contribute to the mysterious phenomenon we call dark energy, which is believed to be pushing the universe apart faster and faster. So no, space is not just the place where you lose your keys or send your thoughts during awkward conversations. It is alive with structure and movement, even when there's nothing visible to the eye. And it gets even stranger when you consider that space itself can expand. Not the things in it moving farther apart, but space itself stretching between them. That idea, too, comes from Einstein's theories, and it underpins our modern understanding of cosmology. But let's pause for a moment. It's easy to feel overwhelmed by the idea that the emptiest thing in existence is actually humming with energy and geometry, and fields we can't even see. Yet in a way, that makes it all the more comforting. Because it means that the universe isn't just a cold void. Even in its quietest, darkest moments, there's still something happening. A soft background hum, like the quiet crackle of a fireplace or the rustle of leaves on a still night. And that hum, those fluctuations, that restless vacuum, is a reminder that space isn't just the absence of matter. It is a physical entity with properties of its own. It can bend and stretch, expand and ripple. It has energy. It has temperature. In fact, even the vast emptiness between galaxies is thought to be just a few degrees above absolute zero, still faintly warmed by the leftover glow of the Big Bang. So when we ask, what is space? We're not talking about an empty void. We're talking about a rich, structured fabric that connects every atom, every galaxy, every living being. Space is not where things happen. Space is one of the things that happens. It's part of the story, not just the stage. And maybe that's the strangest thing of all. The more we study space, the more it refuses to be empty. It twists, it hums, it fluctuates, it expands. Even when it seems to do nothing, it's never really doing nothing at all. And as for those missing socks, well, space might not be to blame. But if they did fall into a pocket of warped space-time, at least they'd be part of a very exclusive scientific mystery. Imagine standing on a quiet hilltop under a clear night sky, gazing up at a universe that stretches in every direction. It feels endless, infinite, eternal. But what if I told you that there's a cosmic limit to what you can see? A kind of celestial bubble that surrounds us, not because the universe ends there, but because light simply hasn't had time to reach us from beyond. This isn't science fiction. This is the observable universe, and it's the part of the cosmos we can actually detect. Light, radiation, gravitational waves, anything that has managed to travel to us since the beginning of time. That word observable is key. It doesn't mean that everything outside of it doesn't exist. It just means we're not lucky enough to have seen it yet. Now here's where things get interesting. You might think, logically, that the farthest we could possibly see would be about 13.8 billion light-years away. After all, that's how long the universe has been around, give or take a few 100 million years. And if light moves at, well, the speed of light, wouldn't that be the edge of our vision? If only the universe were that straightforward. Because of the way space itself expands, that boundary is actually much farther out. What we call the observable universe has a current radius of about 46.5 billion light-years in every direction, making it roughly 93 billion light-years across. Yes, you heard that right. Even though the universe is only 13.8 billion years old, the distance to the farthest galaxies we can see is more than 3 times that. Because space has been stretching the whole time. Think of it like this. Imagine placing raisins on a loaf of bread and popping it in the oven. As the bread rises, the raisins move farther apart. Now imagine a photon of light is emitted by one raisin toward another right as the baking begins. By the time the light arrives, the bread has expanded. The photon's journey wasn't across a static distance. It was across a growing one. The destination moved farther away as the light was en route. That's more or less what happens on the grander scale. This brings us to the concept of the cosmic horizon. It's not a wall, You're not going to fly a spaceship out there and suddenly bonk into the edge of the universe like a cosmic cartoon. Instead, it's more like a gentle fading of information. Beyond this horizon, light from distant regions hasn't had enough time to reach us since the Big Bang. It's as if we're standing in a vast fog, only able to see the nearby glow. The rest is shrouded, not because it's not there, but because the universe hasn't given us the signal yet. This horizon forms the boundary of our observable universe, and it's always changing. As time goes on, light from more distant regions will arrive, and the bubble will expand. At the same time, because of the accelerating expansion of space, some galaxies are moving away from us so quickly that the light they emit now will never, ever reach us, not even in trillions of years. They're receding faster than light itself, not because they're breaking any cosmic speed limit, but because the space between us is stretching too fast. In a very real sense, the universe is slipping out of our grasp. Now let's take a gentle pause to appreciate something beautiful. Every single star, every galaxy, every smudge of light we see in the night sky is within our observable universe. That's the good news. The bad news? There's almost certainly far more beyond it, maybe infinitely more, that we'll never see, touch, or study. We're surrounded by a vastness that mocks our instruments, and yet we can only peek through this little bubble of perception. What's even more humbling is that everyone, everywhere, has their own observable universe. If you were standing on a distant galaxy 10 billion light-years away, your cosmic bubble would overlap ours a bit, but it would also include regions we'll never know. In other words, the observable universe isn't the universe. It's just our slice of it. And what a slice it is. Roughly 2 trillion galaxies, each containing millions to trillions of stars. That's a lot of starlight crammed into our little observational bubble. The photons from some of these galaxies have been traveling for billions of years, only to be finally absorbed by the back of your retina or your telescope sensor tonight. Some of that light began its journey before Earth had even formed. That ancient glow is a kind of time machine, a message in a bottle from an epoch long past. And yet, as rich as this observable universe is, it may represent only a tiny fraction of the total universe. Beyond the cosmic horizon, space might continue forever. It might be curved or flat or even loop back on itself in some strange multidimensional geometry. But we'll never know. Not with light, not with any signal bound by time and the speed of causality. There's a kind of peacefulness in that limit. Knowing we can't see everything reminds us that our place in the cosmos is fundamentally local. We don't have to understand or control the whole universe to find meaning in it. Sometimes it's enough just to sit beneath the stars and know that you're part of something much, much larger than yourself. And while 93 billion light-years sounds massive, and it is, it's also just the visible frosting on an unfathomably big cosmic cake. What lies beyond? We can only guess. Maybe more galaxies, more structure, more dark matter and dark energy. Or maybe something stranger still. But for now, we're here, drifting inside a glowing bubble of light, information, and time. A bubble shaped not by borders, but by the patient journey of photons and the limits of cosmic time. It's not a prison, it's a gift. A slowly expanding gift that lets us see deeper into the story of the universe with every passing day. When we look up at the night sky, we often imagine that we're seeing the universe as it is right now, but that's not quite true. What we're really seeing is the universe as it was. Every star, every galaxy, every glowing dot in the sky is a time capsule. The farther away it is, the older the light we're seeing. In fact, looking across the universe is a bit like rummaging through a cosmic attic. Each layer of light takes us deeper into the past. Let's start with the humble light year. A light year is the distance that light travels in 1 year, about 6 trillion miles or nearly 10 trillion kilometers. When you look at a star that's 100 light years away, the light reaching your eyes left that star 100 years ago. You're seeing it not as it is, but as it was when your great-grandparents were still young. Now stretch that idea across the vast expanse of space. Some of the galaxies we observe are billions of light years away. That means the light we detect from them began its journey before our solar system even existed. Long before Earth formed its oceans or developed its first microbial life, that light was already racing toward a future observer, toward you. This leads us to something astronomers call look-back time. It's a way of expressing how far into the past we're seeing when we observe distant objects. If a galaxy is 8 billion light-years away, its look-back time is 8 billion years. That light has been travelling across space for more than half the age of the universe, arriving just in time to illuminate your evening stargazing or to land on the mirrors of a telescope orbiting above Earth. In a strange way, space is full of ghosts, echoes of what once was. We're not seeing galaxies as they are today. We're seeing them frozen in earlier chapters of their existence. Some of them may not even exist anymore. They might have merged with other galaxies, changed shape, run out of star-forming gas, or simply drifted beyond the reach of light due to the expansion of space. What we see is a kind of cosmic fossil record, written in photons. But it gets even more fascinating. As light travels through the expanding universe, it stretches. This phenomenon is known as redshift. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelength of light lengthens when its source moves away. Since space itself is expanding, nearly all distant galaxies are receding from us, and the light they emit becomes stretched into longer, redder wavelengths as it travels. Hence the name redshift. By measuring the amount of redshift in the light from a galaxy, astronomers can determine how far away it is, and more importantly, how long that light has been on its journey. A high redshift means a very distant galaxy, and a very ancient glimpse into the early universe. This redshifted light holds clues about the structure, age, and history of the cosmos. It tells us how fast the universe is expanding, how galaxies evolve, and even hints at the mysterious forces like dark energy that are shaping everything on a grand scale. Every color-shifted photon is a little messenger from the past, carrying encoded stories of where it came from and what the universe was like back then. Now let's talk about telescopes, our cosmic time machines. When you look through a telescope, you're not just seeing things more clearly, you're seeing them more deeply into time. A backyard telescope might show you Jupiter's clouds from about 40 minutes ago. A more powerful observatory could show you a galaxy as it appeared 500 million years in the past, back when life on Earth was still experimenting with fins and gills. Then we have the heavyweights, the great observatories like Hubble, James Webb, and future successors waiting in the wings. These instruments can peer so far into space, and thus so far back in time, that they capture the faint light of the first galaxies to ever form. We're talking about structures that began taking shape just a few 100 million years after the Big Bang. It's a little ironic that in our quest to understand the future of the universe, we have to spend most of our time staring into its past. But that's the nature of light. It travels fast, but not instantly. And because the universe is so vast, even light has to work hard to keep up. This means the universe, as we experience it, is always a little out of date. It's like watching a film that's still being edited, with scenes arriving one at a time, out of chronological order, some from galaxies just next door and others from across the cosmic abyss. Yet that delay is a gift. Without it, we'd never be able to piece together the story of how everything came to be. The slower arrival of ancient light lets us see different stages of the universe's evolution all at once, like pages torn from a novel and scattered across the sky. The result is a kind of beautiful patchwork of time. In one direction, we might see a relatively nearby galaxy that formed recently. In another, we might glimpse a flickering light from billions of years ago, when stars were still forming from clouds of primordial gas. All of these images are layered not just across space, but across time itself. You could say we're living inside a museum made entirely of light, but instead of walking from exhibit to exhibit, we let the photons come to us, crossing unimaginable distances to tell their stories, to fill our sky with ancient news from the dawn of everything. There's something quietly poetic about this idea, that every time you look up you're gazing into a time machine, that the light brushing against your eyes may have started its journey before the first tree on Earth, before the first cell, before the first breath of atmosphere. And all of this All these insights come from simply listening to the light. By studying its colors, its shifts, and its age, we unlock a silent language spoken across billions of years, a language that doesn't just describe the universe, it is the universe encoded in motion and memory. Next time you see a star twinkling above, remember that you're not looking at it as it is. You're looking at a version of it preserved in time, a glimmer of history still racing through the darkness. You're seeing what the universe looked like when it was younger, smaller, perhaps even gentler. And through the lens of science and with the patient help of light, we continue to piece together our origin story, one distant glow at a time. Picture yourself standing in a field early in the morning. The grass is still wet with dew, the air is cool, and a soft fog rolls gently across the horizon. You can only see a short distance ahead, maybe a few trees, the outline of a distant hill. But beyond that, everything fades into a pale blur. You know the world continues past the fog, but your vision can't reach it just yet. In a way, that's what it's like to live inside the universe. No matter how powerful our telescopes become, there's a limit to how far we can see. Not because of fog in the traditional sense, but because of time, distance, and the peculiar nature of the expanding cosmos. These limits are what we call cosmic horizons, and they define the boundaries of our observable universe. Now, unlike the tidy horizon on Earth where sky meets land, cosmic horizons come in a few different flavors, each with its own rules and significance. The first is called the particle horizon. Think of it as the maximum distance from which light or any other signal could have reached us since the universe began. It marks the outermost edge of the observable universe, the ultimate limit of our current cosmic bubble. The particle horizon is shaped by time itself. Since the universe has existed for about 13.8 billion years, and because space has been expanding during that time, the furthest distance light could have traveled to reach us today is around 46 billion light-years in any direction. That's why the observable universe is roughly 93 billion light-years across. It's the grand perimeter of everything we can currently detect. But don't mistake this horizon for a wall. There's no border, no glowing edge with a no-entry sign. Instead, it's a limit woven into the very fabric of time. Like standing on the shore of a vast sea, you can look out as far as the light allows, but you'll never see beyond that gentle curve. Not because there's nothing there, but because the signals haven't had time to arrive. Next, we come to the event horizon of the universe, not to be confused with the dramatic kind surrounding black holes. In cosmology, the event horizon refers to the boundary beyond which events cannot ever affect us, no matter how long we wait. It's the cosmic line in the sand. Anything beyond this point is retreating from us faster than the speed of light due to the expansion of space. That light, no matter how persistent or patient, will never catch up to us. It's a little bit like trying to send a message to a friend on a raft floating away down a river. You throw a bottle with a note inside, but the current is so strong that the raft drifts faster than the bottle can reach it. No matter how hard you try, the message will never be delivered. That's the event horizon, where communication, even light itself, becomes impossible. At this very moment, the cosmic event horizon is thought to be around 16 billion light-years away. That means there are regions of the universe we can see now, but if those regions emit new light today, that light will never reach us. We're watching galaxies that are, in a very real sense, slipping away, visible today, but destined to fade from view forever. Finally, we have the cosmological horizon, which is sometimes used interchangeably with the particle horizon, but can also refer to more general boundaries in space-time. It's a term that encompasses these observational limits and reminds us that horizons aren't just visual. They're deeply tied to the physics of the universe itself. The cosmological horizon can be thought of as the moving edge of the observable universe, expanding outward as time goes on and light from more distant objects has the chance to arrive. These horizons are constantly shifting and evolving. As the universe ages, the particle horizon grows. More light has time to reach us. But because of dark energy and the accelerated expansion of space, the event horizon shrinks in relevance. More galaxies move beyond our reach. The universe becomes a place of increasing isolation, not because it's empty, but because the light from its distant corners is falling behind. To put it another way, the universe is like a slowly inflating balloon. Dots on its surface drift apart, and the farther they are, the faster they move away. We can only see the dots close enough for their light to make the trip. Beyond that, the light stretches and dims until it vanishes into the expanding abyss. There's something haunting but also peaceful about these limits. It's a quiet reminder that we're not omniscient observers. Our view is shaped by cosmic history, by how long light has been traveling, and by the strange properties of the space it travels through. We're peeking through a window that's enormous, yes, but still finite. Some regions of the universe will always remain a mystery, no matter how patient or clever we become, not because we lack technology, but because of the very nature of space-time itself. These unseen realms aren't behind a curtain waiting to be pulled back. They are beyond the reach of information, forever unknowable, and yet, even within these boundaries, we've managed to learn so much. We've mapped galaxies, measured background radiation, and traced the fingerprints of the Big Bang. We've used the fog of the particle horizon to understand the structure of the cosmos, and the glow of ancient light to piece together its story. The horizons don't limit our imagination, they frame it. Like the rising sun burning off the morning mist, every new discovery pushes the fog back just a little, revealing more of the landscape, but some parts will always remain hidden behind the curve, behind the stretching, swelling boundary where light will never arrive. Still, here we are, spinning quietly in a corner of the universe, watching photons arrive from billions of years ago, reading the messages they carry, and dreaming about what lies beyond the next soft bend in the cosmic road. Even if we can't see it all, even if parts of the universe are forever beyond our reach, the beauty is in the trying, in listening to the quiet hum of light, in following it to the edges of knowledge, and in knowing that while we may never see the full view, we're part of the story just the same. Not too long ago, in the grand timeline of human curiosity, people believed the universe was pretty steady. Galaxies were out there, stars were shining, and everything more or less stayed put. A quiet, eternal cosmos. But in the early 20th century, a game-changing discovery quietly rose from a mountaintop observatory, and the universe hasn't sat still since. It was Edwin Hubble, yes, the same name we gave the famous space telescope, who first noticed something peculiar. While studying distant galaxies, he observed that their light was consistently redshifted. That meant the galaxies were moving away from us, and the farther away they were, the faster they seemed to recede. This wasn't a random trend or a cosmic coincidence. It was a pattern, a law. Space itself, it seemed, was expanding. Now, this isn't quite the same as galaxies zooming through a fixed, static space like cosmic race cars. It's not like they're bursting outward into a pre-existing void. What's actually happening is stranger and more elegant. Space itself is growing. Imagine that space is the thing stretching, and galaxies are being carried along with it, like raisins embedded in a rising loaf of bread. That image, raisin bread, is a gentle and surprisingly accurate way to picture it. Think of the dough as space, and the raisins as galaxies. As the dough bakes and rises, it stretches in every direction. Each raisin finds itself farther from the others, not because it's moving on its own, but because the dough between them is expanding. There's no central raisin, no preferred direction, just a uniformly growing loaf. This is how the universe works on a large scale. Galaxies aren't rushing outward through space like cannonballs. They're being carried away from each other as the fabric of space itself stretches. That's why, no matter where you are in the universe, it looks like everything else is moving away from you. From every galaxy's point of view, space is expanding in all directions. It's a bit like being in a rising souffle. No matter which bubble you're in, all the other bubbles seem to be drifting away. The universe isn't expanding into anything, it's just expanding. There's no outer shell, no edge it's racing toward. Instead, the distances between unbound objects simply grow over time, as if the cosmic measuring tape is slowly lengthening. This idea of an expanding universe was so radical when Hubble proposed it that even Albert Einstein had to revisit his own equations. Originally, Einstein had added something called the cosmological constant to his general theory of relativity to make the universe stand still. He thought the cosmos had to be static, and his equations, left to their own devices, suggested otherwise. When he heard about Hubble's findings, he famously called the addition of the constant his greatest blunder, though ironically, the concept has since made a comeback in explaining dark energy. The universe has a sense of humor too, it seems. But back to the expansion. One of the most beautiful consequences of Hubble's discovery is that it allowed us to rewind the cosmic clock. If galaxies are all moving away now, they must have been closer together in the past, much closer. This led scientists to the idea of a hot, dense beginning to the universe, what we now call the Big Bang. The term Big Bang can be a little misleading. It wasn't an explosion in space, like fireworks going off in a dark field. It was more like the rapid swelling of space itself, everywhere, all at once. No center, no blast radius, just the entire universe, suddenly stretching out of a state of extreme density and heat. You can't point to a location in the sky and say, that's where the Big Bang happened, because it happened everywhere, including right where you're sitting. That expansion is still going on today. Nearly 14 billion years later, galaxies continue to drift apart, and the light they emit continues to stretch with them. The farther away something is, the more its light gets redshifted by the expanding universe. It's a cosmic stretching of time and space that shapes every observation we make. Interestingly, the universe's expansion doesn't affect everything equally. It works on the grand scale, between galaxies and galaxy clusters. But it doesn't pull your morning coffee farther from your lips or separate the atoms in your chair. That's because gravity and other forces dominate on smaller scales, keeping things nicely glued together. The Milky Way isn't expanding. Your neighborhood definitely isn't expanding. And unless your washing machine is eating socks again, even your laundry pile is relatively stable. But on the cosmic level, the expansion continues, and what's more, it's accelerating. This discovery, made in the late 1990s, came as a surprise. Scientists had assumed that the expansion might be slowing down due to gravity. Instead, they found that some mysterious force, now called dark energy, is causing it to speed up. The dough isn't just rising, it's rising faster and faster with every passing moment. No one's entirely sure what dark energy is. It might be an inherent property of space itself, or a field we haven't yet understood. But whatever it is, it now dominates the energy budget of the universe. That gentle stretch is turning into a cosmic sprint, and galaxies are receding from one another at ever greater speeds. It's a little poetic in a quiet way. The universe began with everything close together, dense and unified. Over time, it expanded, cooled, formed stars and planets, and all the ingredients for life. And now it continues to drift outward, stars aging, galaxies moving apart, space stretching into the unknown. Like a story that opens with a bang, blossoms into complexity, and drifts off into a gentle, infinite epilogue. There's no sound in space, but if there were, maybe it would be the soft creak of rising dough, the occasional pop of a bubble, the slow shift of warm expansion. Not a violent noise, not a shout, just the peaceful hum of a universe becoming itself. So when we say the universe is expanding, we're not talking about things flying away from some central point. We're talking about the very fabric of reality stretching, as calmly and steadily as a loaf of bread in the oven. It's one of the most profound discoveries in science, and also one of the most comforting. The idea that change can be slow, steady, and beautiful. And as we sit here, surrounded by stars and bathed in ancient light, we're part of that expansion. Every breath, every heartbeat, every thought you've ever had has taken place on a little rock spinning in the middle of rising cosmic dough. It's enough to make you hungry for answers, or at least for a midnight snack. In physics, there's a hard and fast rule that's never meant to be broken. Nothing can move faster than light. Not a spaceship, not a signal, not even your cousin Greg who claims he once dodged traffic by running across 6 lanes in record time. According to Einstein's theory of relativity, the speed of light, about 299 million meters per second, is the universal speed limit. and nothing with mass can ever reach or exceed it. And yet, out there in the great cosmic distance, astronomers have observed something that seems to defy this rule. Galaxies that appear to be moving away from us faster than the speed of light. Entire clusters of stars and dust slipping beyond our grasp at superluminal speeds. It sounds like physics should be panicking, but don't worry, everything's fine. The universe isn't breaking the rules, it's just playing a very clever game with them. To understand what's going on, we need to revisit a key idea. Galaxies are not flying through space like comets in a vacuum. Instead, space itself is expanding, and galaxies are being carried along with it. Think of space as a rubber sheet with dots on it. If you stretch the sheet, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is growing underneath them. This is how galaxies can appear to recede from each other faster than light. It's not that they're breaking the speed limit, it's that the space between them is stretching so quickly that the total separation increases at a rate greater than light can bridge. The galaxies themselves remain obedient little citizens of physics. It's space that's doing the legwork. Here's a helpful way to picture it. Imagine you're standing on a treadmill that's gradually speeding up. You try to walk towards someone at the other end, but the treadmill is moving backward faster than you can walk forward. Eventually, no matter how hard you try, the distance between you and the other person keeps increasing. It's not that you're walking too slowly, it's that the ground beneath you is working against your motion. In the case of the universe, light is trying to travel through expanding space. But in some regions, especially very far away, space is expanding so rapidly that the light never makes progress toward us. It's like trying to paddle a canoe upstream during a flash flood. The water flows too fast and your boat is swept farther away despite your best effort. This doesn't violate relativity because that theory only forbids objects moving through space faster than light. It doesn't say anything about how fast space itself is allowed to grow, and it turns out space has quite the flair for dramatic entrances. Take, for example, a period called cosmic inflation. This was a mind-bendingly brief moment just after the Big Bang when the universe expanded at an absolutely staggering rate, far faster than the speed of light. In less than a trillionth of a second, the universe grew from something smaller than a proton to something the size of a grapefruit, or possibly larger. Try explaining that expansion in a recipe. And again, this faster-than-light swelling didn't break any rules. It was space doing the expanding, not particles racing through it. It's one of the few times in physics when faster-than-light travel is not only allowed but encouraged. Just don't try it in a spaceship. Your engines will not appreciate the suggestion. This rapid inflation smoothed out the early universe, ironing away wrinkles and unevenness like a cosmic steam press. It also helps explain why the universe looks so uniform in every direction, despite the fact that distant regions haven't had time to exchange information. Inflation spread everything out so quickly that local differences became subtle and stretched far apart. Even now, billions of years later, we're still seeing the effects of that expansion. Space continues to grow, carrying distant galaxies farther and farther away from us. Some of those galaxies are now receding faster than light, not because they're speeding up, but because the space between us is growing faster than light can close the gap. This means that there are regions of the universe we can never see, no matter how long we wait. Their light will never reach us, and if they emitted new light today, that light would be swept away into the deepening void. These galaxies aren't lost because they're moving too fast. They're lost because the road between us is stretching out faster than their signals can travel. It's a bit like trying to send a postcard across a river where the opposite shore is drifting away faster than you can throw. No matter how many stamps you stick on it, the postcard is never going to make it. Eventually, even the idea of delivery becomes meaningless. So, when astronomers say some galaxies are receding faster than light, what they mean is this. Due to the expansion of space, the separation between us and those galaxies is increasing at a rate faster than light can keep up with. There's no violation, no rebellious physics, just a clever interpretation of how space and time can flex in ways our instincts don't always understand. In fact, this cosmic trick has another strange consequence. There are galaxies we can see today, clear as day through our best telescopes, that have already crossed this horizon. They are still visible because the light they emitted long ago is still arriving, but their newer light, being produced now, is already out of reach. It will never get to us, not even if we wait an eternity. It's a little like watching the taillights of a car that's just turned a corner. You can still see the glow, but the car itself is already gone, cruising down a road you'll never follow. The light is a ghost, a message from a past that can no longer be updated. This reality has a certain peaceful melancholy to it. The universe is full of stories we'll never hear, stars we'll never see, galaxies we'll never know existed. Not because we didn't look hard enough, but because the cosmos itself is drawing the curtain, stretching the stage beyond our view. Yet this too is part of the wonder. The fact that we've been able to glimpse so much of the universe's past is nothing short of miraculous. Despite all the distance and distortion, we've still managed to see billions of light years in every direction. We've caught ancient photons in mid-flight, pieced together the origins of galaxies, and even traced the faint afterglow of the Big Bang itself. And all of this has happened from a tiny planet orbiting an unremarkable star in an average galaxy, in a universe where space moves faster than light. It's enough to make you feel small, but also strangely lucky, because here we are, listening to the whispers of an expanding cosmos, watching light struggle to reach us, counting galaxies as they fade into the distance, and all the while, the dough of the universe continues to rise, carrying with it the dreams of curious beings who once wondered just how far light could go. When we think about the universe, it's tempting to picture it like a big black box, a vast rectangular space with a top and bottom, left and right, front and back, just floating in something. Maybe it has edges, maybe it goes on forever, maybe there's a giant cosmic wall with a do not enter sign and a very bored security guard. But the real shape of space is much more subtle and much more fascinating. It turns out that space isn't necessarily flat like a tabletop. It might be curved. In fact, it might be positively or negatively curved, or just ever so gently flat. And this isn't just a matter of aesthetics. The geometry of the universe has deep implications for how it evolved, how it behaves, and whether it might one day curve back in on itself or continue stretching forever. Let's start with the three main possibilities. The first is a flat universe, like an infinite sheet of paper. In this model, the rules of geometry behave just as we learned them in school. Parallel lines never meet. Triangles always add up to 180 degrees, and if you travel in a straight line, you'll never loop around. You'll just keep going indefinitely through an endless cosmic plane. The second option is a closed universe, shaped like a sphere, or more precisely, the three-dimensional equivalent of a sphere. Here, space curves back on itself. If you were to set off in a straight line in any direction, and somehow avoided stars, planets, and all other space debris, you would eventually return to your starting point. Like walking in a straight line around the surface of the Earth, you wouldn't fall off. You'd just keep going in circles, though it might take several billion years and an industrial-strength pair of shoes. The third possibility is an open universe, shaped like a saddle. This space curves outward, like a Pringle. In this geometry, parallel lines eventually diverge, triangles add up to less than 180 degrees, and if you tried to go around the universe, you'd never come back to where you started. You'd simply drift farther and farther out into the cosmic vastness. These shapes, flat, closed, and open, are not just abstract ideas, they're tied directly to the universe's overall density and energy content. Specifically, how much matter and energy exist compared to what would be needed to make the universe perfectly balanced. This critical density determines whether space bends inward, outward, or not at all. If the actual density is greater than the critical density, space is closed and positively curved. If the density is less, it's open and negatively curved. And if the densities match just right, the universe is flat. It's a bit like the Goldilocks of cosmology, not too much, not too little, but just enough to keep the geometry straight. And how do we measure this? As it turns out, the universe leaves behind clues in the cosmic microwave background. the ancient light that's been travelling since shortly after the Big Bang. By analysing the tiny fluctuations in this faint glow, scientists can determine how space bends light over vast distances. It's like using the pattern of ripples on a pond to understand the shape of the shore. So far, the evidence suggests something remarkable. Our universe appears to be very, very close to flat. Not perfectly flat perhaps, but close enough that any curvature is too small to detect with current instruments. It's like standing on a massive plane that might have a slight bend somewhere over the horizon, but as far as you can see, it's pretty straight. Now, here's where things get really interesting. A flat universe can still be infinite, or not. And a closed universe, surprisingly, can be finite but unbounded. That phrase sounds like a contradiction at first, like saying you have a mug that's full but holds no coffee. But it makes sense with a little thought. Take the surface of a sphere. It's finite. You can measure the total area, but it has no edges. You can walk around the surface of a globe forever and never fall off the edge, because there is no edge. The whole surface connects back on itself. Now take that concept and apply it to a three-dimensional version. That's what cosmologists mean by a space that's finite, but unbounded. It's a closed loop, a self-contained bubble of geometry. This kind of space doesn't have a border. There's no place where the universe ends and something else begins. It's just space, curving back around in a grand, subtle loop. And because we live within it, we'd never be able to tell directly. We'd just keep drifting forward, thinking we're going straight, while quietly bending back toward home. Even in a flat or open universe, infinity brings its own peculiar flavor. An infinite universe means an endless number of galaxies, stars, and potentially even repeating patterns. Somewhere out there, if the universe is truly infinite, there could be another version of you listening to this same video, possibly in a slightly different pair of pajamas. Now, it's worth noting that we can only observe a small fraction of the universe. Beyond our observable horizon, we don't know how space behaves. It could be flat forever, or it could curl into a loop we're too small to detect. The curvature might be so slight that even a light beam travelling for billions of years doesn't reveal it. It's like trying to tell whether the Earth is round while standing in a meadow. You don't see the curve, but it's there all the same. Cosmic geometry also affects the fate of the universe. In a closed universe, gravity might eventually slow down the expansion and cause everything to contract, leading to a big crunch. In an open or flat universe, expansion could continue indefinitely, thinning out matter and cooling the cosmos into a gentle fade. Though with dark energy pushing things apart ever faster, the big crunch seems unlikely, at least with what we know today. What's particularly comforting in a quiet kind of way is that no matter the shape, we're part of it. Whether the universe loops or drifts, curves or stretches, we are woven into its structure. Our atoms obey its geometry. Our light traces its curves. Our thoughts echo through its halls. We don't just live in space. We are space, folded into itself in a dance of mass and motion. So if the universe is flat, we live in a grand plane of cosmic possibility. If it's curved like a sphere, we may be looping around inside an invisible bubble. If it's open, we're surfing an endless saddle, heading out into infinity with no round trip planned. Whichever version is true, it's strange, elegant, and beautifully confusing in just the right measure. And that's part of the magic. You don't need to pin down the shape of space to appreciate its mystery. You can simply gaze up, smile at the stars, and know that you're standing on a tiny patch of something grand and curious. A universe with a shape we're still trying to imagine from the inside out. Imagine you're a tiny creature living on the surface of a balloon. You can walk north, south, east, and west along the surface, but you can't dig down or float above it. Your entire world is that two-dimensional skin, curved but seamless. You don't know the balloon is being held by a giant cosmic toddler with a helium tank. You just know that when you walk straight, you eventually loop back to where you started. This is the magic of curved space. It plays by rules that don't always match our everyday experience, and yet it makes perfect sense once you slip into its rhythm. And while we humans live in 3 dimensions of space, Curved surfaces in 2 dimensions give us a surprisingly useful way to imagine what our universe might be doing on a much grander scale. Let's start with something simple. On a flat surface, like a sheet of paper or a calm tabletop, geometry behaves in familiar ways. You can draw a triangle and the angles will always add up to 180 degrees. If you draw 2 parallel lines, they'll never meet. And if you start walking in a straight line, you'll keep going forever, unless you hit a wall or an unfortunate coffee spill. But now imagine walking on the surface of a sphere, say a planet or that balloon we mentioned earlier. Geometry starts acting a little strange. If you draw a triangle using great circles, like the equator and lines of longitude, the angles can add up to more than 180 degrees. Parallel lines. They don't stay parallel for long. They converge at the poles or drift apart depending on the path. Most importantly, if you walk in a straight line on this curved surface, you'll eventually come back to where you started without ever turning around. No edges, no borders, just a continuous loop. From your limited perspective on the surface, the space around you feels infinite, but in reality it's finite and curved back on itself. Now take that concept and scale it up. Imagine our entire universe as a 3-dimensional version of that balloon surface, except instead of curving in 2 dimensions, it's curving in 3, or rather, in a way we can't easily visualize because it curves in higher dimensional space. You and I live inside this 3-dimensional space, moving through it without ever seeing the outside, just like the balloon creature never sees the air around the balloon. In this analogy, the galaxies are like dots drawn on the surface of the balloon. As the balloon inflates, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is stretching. This is what cosmologists mean when they say the universe is expanding. It's not that galaxies are flying through space like comets on holiday. It's that space itself is growing, carrying galaxies with it. And just like our little balloon creature, if the universe is truly curved and finite, then traveling in a straight line long enough might eventually bring you right back to where you began. You wouldn't fall off the edge of space because there is no edge. The loop closes smoothly. It's a finite space with no boundary, which is a strange and lovely idea. You could go on an infinite journey through a finite universe, never hitting a wall, never running out of room. The balloon analogy also helps us understand something else. Why there's no special center of the universe. Just as there's no single center on the surface of a balloon, the universe doesn't have a central point from which everything is expanding. The expansion happens everywhere at once. Every point on the balloon moves away from every other point as it inflates. You could pick any spot and call it here, and the view would look the same in all directions. It's worth pausing here to note that the balloon analogy isn't perfect. It's just a model to help our 3-dimensional brains wrap around a higher dimensional idea. The balloon's surface is 2-dimensional and embedded in 3-dimensional space, which we can see and picture. But if our universe is curved, it might be curved in a higher dimensional space we can't observe directly. It's not floating in a larger container. Space doesn't need an outside to curve. It can curve intrinsically, by its own properties, without reference to anything external. This idea of intrinsic curvature is one of the great insights of Einstein's theory of general relativity. Space, and space-time more broadly, isn't a passive backdrop. It has shape and structure, and that shape can evolve over time. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. It's a beautifully circular relationship, one that governs everything from the orbits of planets to the behavior of galaxies on the larger scales. The curvature of space also affects the path of light. In curved space, light doesn't travel in straight lines as we understand them. It follows the shortest path available, called a geodesic. On a sphere, that's a great circle. In our universe, it's a curved trajectory that bends under the influence of gravity and the shape of space itself. That's why massive objects like stars and black holes can bend light, a phenomenon known as gravitational lensing. So, when we gaze out at the night sky, we're not just seeing objects scattered through flat, empty space. We're seeing a web of light moving through curved space, stretched and bent and shaped by the mass of everything around it. It's like looking at the stars through a slow-moving funhouse mirror, except the distortions tell us something true about the shape of the cosmos. Now let's return to our balloon one last time. As it inflates, the distances between the galaxies on its surface grow. But the galaxies themselves don't expand, they stay the same size. That's because the expansion of space happens on large scales, between objects not gravitationally bound together. So our Milky Way, our solar system, even our planet and its crusty old coffee shops, none of those are getting stretched like taffy. The expansion only takes hold in the great emptiness between galaxies. And what's driving this expansion? Well, we now believe that dark energy, a mysterious form of energy inherent to space itself, is causing the universe to accelerate in its growth. It's like the balloon is not just inflating, but doing so faster and faster with every breath. We don't know exactly what dark energy is, but we can see its effects in the way distant galaxies move and how ancient light spreads across the sky. So where does this leave us? It means we live in a space that might be curved, that might be finite yet boundless, expanding yet centerless, shaped by rules that defy our everyday experience, yet make perfect sense in the grand cosmic dance. And all of this, the curves, the expansion, the possibility of looping back to our starting point, can be imagined with a simple balloon. A rubbery metaphor floating through thought space, whispering ancient secrets about a universe that grows not outward from something, but within itself. Next time you see a balloon rising into the sky, give it a little nod. It may be full of helium and squeaky good fun, but it also carries within it the shape of something much greater. A gentle curve, a stretch of space, and the quiet idea that maybe, just maybe, the place you're headed is also the place you started, only now you've travelled the universe to get there. Infinity. The word itself feels like it should echo when you say it. It's vast, mysterious, and more than a little intimidating. It conjures up images of endless stars, limitless space, and the kind of math problems that make high school students reconsider their life choices. But what does it really mean when we ask, is the universe infinite? Is space truly unending, stretching on forever without a final border or wall, or is there something more subtle going on? Let's start with what we know. So far, everything we've measured about the large-scale structure of the universe suggests that it might be infinite. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, reveal that space is extremely close to being flat. Not bumpy like a sphere, and not curved like a saddle, but flat in a geometrical sense. And in the context of general relativity, a flat universe could very well be infinite. If it isn't, it's at least much, much larger than the portion we can observe. That leads us to the observable universe, the cosmic bubble we can see. It stretches about 93 billion light-years across. That's the part of the universe we have access to because light from those regions has had time to reach us since the beginning of the cosmos. But beyond that, it could keep going. There might be galaxies upon galaxies, cosmic structures we'll never detect, entire regions of space that are forever beyond our view. And here's the thing, we can't actually prove or disprove whether the universe is infinite because we are confined to our observational limits. We're like ants on a beach, looking in every direction and seeing only sand. For all we know, the beach stretches across the continent, or maybe it ends a few dunes over in a tide pool full of curious crabs. We just can't see far enough to know. This raises an important point. We don't measure infinity the way we measure, say, the distance to the moon. You can't stick a ruler on space and keep going until the numbers run out. Infinity isn't a number. It's an idea, a concept. And in science, concepts need evidence. That's where it gets tricky. You can never directly observe infinity. You can only look for signs that space shows no signs of curving back on itself, or ending abruptly, or behaving in a way that implies it loops. So far we've looked in all directions and seen no detectable edge, no sudden drop-off, no cosmic fence with a do not pass sign hanging on it. But that doesn't mean such a thing doesn't exist. It just means it's beyond what we can see. And unless we suddenly invent a telescope that can break the speed of light and outrun the expansion of the universe, that's not going to change anytime soon. The idea of an infinite universe brings with it some very peculiar consequences. If space is truly infinite, then the amount of matter it contains is also likely infinite, or at least so staggeringly large that it might as well be. That means an endless number of stars, planets, comets, clouds of dust, and yes, potentially even life. Somewhere out there, in the farthest reaches of a never-ending cosmos, there might be another planet just like Earth. Maybe it has trees that grow sideways, or oceans that sparkle with strange colors. Maybe it has creatures asking the same questions we are, wondering whether their universe ever stops. And here's where it starts to bend the brain a little. In an infinite universe, if matter is distributed more or less uniformly, then the laws of probability suggest that patterns will eventually repeat, which means that somewhere out there could be a version of you, or several. Some may be nearly identical. Others might have chosen a different breakfast cereal this morning and accidentally altered the course of their entire day. Now don't worry, this isn't meant to be unsettling. You're not going to bump into your cosmic doppelganger at the grocery store. These regions are likely so far away that they are forever unreachable. The light from those parts of space will never, ever reach us, even if we wait longer than the age of the universe multiplied by every grain of sand on Earth. Still, the implications are profound. Infinity isn't just a matter of size, it's a shift in thinking. It transforms the universe from something large to something boundless. You no longer have to wonder what's beyond the edge of the map, because there is no edge, just more map. Forever. Of course, there are good scientific reasons to be cautious about assuming the universe is infinite. We have only a finite sample to work with, and cosmologists remain open to the idea that space might be very large but still finite. It could curve gently back on itself in a way we can't yet detect, looping through higher dimensions, or forming a shape more exotic than we've ever imagined. There's also the question of time. The universe might be infinite in space, but finite in duration. It had a beginning, what we call the Big Bang, and while the notion of a beginning is itself slippery, it suggests that even if the cosmos is endless in extent, it has not always existed in its current form. Philosophically, infinity challenges the way we relate to the universe. Most things in our daily lives have limits. Our time, our energy, the number of cookies in the jar. Infinity breaks that mold. It removes the boundaries and opens up a playground of endless possibility. That can be inspiring or overwhelming, or both at the same time. Some ancient thinkers were deeply uneasy with the idea of infinity. Aristotle, for example, believed the universe must be finite, because actual infinities were just too strange to accept. And even today, some scientists and philosophers debate whether true infinities can exist in the real world, or whether they're just useful abstractions. But whether or not the universe is infinite, contemplating it has value. It stretches the mind, invites humility, and reminds us how small our perspective really is. When you look up at the stars, you're peering into a mystery so vast that even our boldest measurements barely scratch the surface. You're seeing only a local glow, a few lights in the window of the cosmic mansion, and yet, here we are, tiny creatures on a spinning planet wondering how far space goes. We build instruments to chase ancient light, we invent math to frame the impossible, and we lie awake at night thinking about what lies beyond the last star we can see. Maybe the universe is infinite, maybe it's not. Either way, it's more than enough. More than enough to fuel our questions, our stories, our science, and our dreams. More than enough to remind us that we're part of something truly immense. And the most wonderful part of all, you don't have to know how far it goes to feel at home in it. You're already woven into its fabric, a flicker of thought on the edge of the observable, glowing softly in a cosmos that may never end. There's something irresistible about the idea of an edge. We grow up with edges, walls, fences, sidewalks, lunchboxes. Everything we encounter seems to stop somewhere. So when we think about the universe, it's only natural to imagine it must stop too. Surely after some truly staggering distance, space must come to an end, like the final room in a very big mansion, or the edge of a massive tabletop hanging over the abyss. But here's the twist. Space doesn't actually need an edge. It can be finite in size without having a boundary at all. And that's where things get beautifully strange. Let's start with something simple. Picture the surface of the Earth. If you were to walk in a straight line in any direction, you'd eventually circle back to where you started. You wouldn't fall off anything. You wouldn't hit a wall, and you wouldn't find a signpost reading "End of Earth, please turn around." The surface is finite but unbounded. It loops back on itself in a seamless way. Now take that idea and expand it to a three-dimensional space. Imagine living inside a volume of space that wraps around itself in much the same way the surface of a globe does in 2 dimensions. If you could keep moving forward in a perfectly straight line through this space, you might eventually return to your starting point, having never encountered a wall, cliff, or any kind of edge. This kind of space is not science fiction. It's a perfectly valid model in cosmology. It's called a finite unbounded space. It sounds like a paradox at first, like saying a cup can be full of tea, but not contain any liquid. But once you understand the geometry, it clicks into place. Space can be shaped in such a way that it closes in on itself, forming a complete volume without ever needing to end. One of the classic shapes used to illustrate this idea is the torus. Imagine a donut, not the jelly-filled kind, but the smooth, round kind with a hole in the middle. The surface of the donut is 2-dimensional. You can walk around it without leaving the surface, but it has no edges. It loops back on itself both horizontally and vertically. If you're an ant walking on the donut, you can go forever without ever hitting a boundary. Now imagine a 3-dimensional version of that, where space loops in multiple directions. This doesn't mean the universe is shaped like a pastry, but the torus helps us visualize how space might behave if it were finite and without a border. You could start at one point in space, travel in a straight line, and, after a very, very long time, find yourself right back where you began, like a galactic boomerang. Another helpful analogy comes from video games. In certain classic arcade games like Pac-Man or Asteroids, if you move your character off the edge of the screen on one side, they reappear on the opposite side. It's not that there's an invisible tunnel, they've just looped around on a map that wraps back on itself. These are 2-dimensional versions of a toroidal space. The game world is finite in size, but the edges don't behave like real-world walls, they connect. In theoretical cosmology, this idea is more than just playful musing. Some models propose that the universe could have a topology, its fundamental shape, that loops back in subtle ways. We might not notice these loops unless we look far enough and in just the right direction. There's even been speculation that if the universe is small and curved just right, we might see repeated patterns in the cosmic microwave background, like mirrored wallpaper left behind from the Big Bang. So far, we haven't found any clear signs of this repetition, but the idea hasn't been ruled out completely. The deeper truth is that the universe doesn't need an outer surface or a surrounding void. That's a very human way to look at space, as something sitting inside something else. But space isn't a thing embedded in a bigger thing, it is the thing. It's not like a balloon floating in the air, it's more like the entire balloon itself, with all of us stuck on its surface, unable to step outside and look in. Even if the universe is infinite, it still doesn't require an edge. Infinity isn't a place, it's a property. Saying the universe is infinite is like saying numbers never stop. You don't need to find the last number to know that one doesn't exist. Likewise, you don't need to locate the edge of space to know there might not be one. Edges also create philosophical headaches. If there were an edge, what would be beyond it? More space? Something else entirely? A blank nothingness that sits awkwardly, waiting to be defined? The moment you introduce an edge, you introduce a paradox. If there's something beyond, then space hasn't really ended, and if there's truly nothing, then how can it be said to exist at all? By contrast, a universe without edges avoids this confusion entirely. It just is. You can keep moving forever, or maybe come full circle. There's no edge to fall off, no cosmic warning signs, and no need to define what's beyond the beyond. This doesn't mean we'll never stop asking about boundaries. Our brains are wired to think in terms of containers. We like beginnings, middles, and ends. But the universe doesn't seem to care much for our mental filing cabinets. It stretches, curves, and possibly loops, all without offering a clean border to sign off on. Interestingly, even if space has no edges, time might. Our universe had a beginning, at least from our perspective, with the Big Bang around 13.8 billion years ago. That's not a point in space, but a point in time, a moment when space itself began expanding from an earlier state. Asking what came before the Big Bang is like asking what's north of the North Pole. It's not that the question is meaningless. It's that our usual coordinates stop working. All of this paints a picture of a universe that's far more subtle and strange than a giant box. It's not an object you can lift the lid on or peek around the side of. It's more like a melody that plays itself forward, wrapping around dimensions and humming through time with no final note, no ending chord, just an endless variation. And in that melody, there are no hard edges, only connections, curves, and continuations. Whether it loops or stretches infinitely, the universe doesn't close off like a room, it opens up like an idea. Not bounded by walls, but shaped by relationships, gravity, light, motion, time. Thus, so if you've ever imagined a spaceship sailing bravely toward the edge of the universe, picture this instead. A long, quiet journey that never finds a cliff, only more stars, more questions, and more space. Not because the universe goes on forever, necessarily, but because it never had an edge to begin with. Before there were stars, before there were galaxies, even before atoms had properly settled into their roles, there was a glow, a soft, uniform light spread across the universe like a warm fog, stretching in every direction. It wasn't a spotlight or a flashbulb or a fireworks show. It was quieter than that, gentler, like the first rays of dawn seeping through a window before anyone's had a chance to open their eyes. And some of that light is still with us today. We call it the cosmic microwave background, or CMB for short. It's not just the oldest light we can see, it's the oldest light anyone can see. A whisper from the very early universe, still drifting gently through space, passing through galaxies, stars, planets, and sometimes, with the right instruments, into our detectors. To understand where this light comes from, let's go back in time, way back. About 13.8 billion years ago, the universe began in a hot, dense state, a singularity of seething energy and unfathomable temperature. In its earliest moments, space expanded rapidly, spreading out the energy like batter in a pan. As the universe grew, it cooled, not quickly, but steadily, like a cosmic kettle slowly taken off the stove. At first, the universe was a blinding soup of particles and radiation. Photons, the particles of light, bounced around constantly, trapped in a fog of charged particles. Electrons and protons whizzed around separately, and light couldn't get very far before being scattered in a new direction. Imagine trying to shine a flashlight through a dense cloud. That's what the universe was like for its first few 100,000 years, opaque, chaotic, and full of restless motion. But then something magical happened. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This moment is poetically called recombination, and it changed everything. With fewer charged particles to scatter off, light was suddenly free to travel. The fog lifted. The universe became transparent, and the first light broke loose. That ancient light, set free across the cosmos, has been traveling ever since. It fills the universe in every direction, stretched out by billions of years of cosmic expansion. Once a searing blast of ultraviolet energy, it's now cooled to a gentle microwave hum, a whisper instead of a roar. But it's still there, all around us, passing through your room this very moment like a soft, invisible breeze from the beginning of time. We first discovered the CMB almost by accident. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were using a large horn-shaped antenna to study radio signals. They kept detecting a persistent background noise, no matter where they pointed their antenna. They cleaned the equipment, double-checked their math, and even removed some pigeons nesting in the device, just in case it was their fault. But the noise remained, steady, uniform, and strangely cosmic. What they had stumbled upon, without realizing it at first, was the afterglow of the Big Bang. It was the cosmic microwave background, predicted by theory, and now detected in all its subtle glory. That faint hiss on their radio signal turned out to be a window into the infant universe. Since then, scientists have mapped the CMB in astonishing detail. Space missions like COBE, WMAP, and most recently the Planck satellite have given us a high-resolution picture of this ancient light. And what they revealed is more than just a glow. It's a cosmic blueprint, a snapshot of the universe when it was less than 500,000 years old. At first glance, the CMB looks incredibly uniform, the same temperature and brightness no matter which way you look. But zoom in closely and you'll see tiny fluctuations, little warm and cool spots just a few millionths of a degree different from each other. These gentle ripples aren't imperfections. They're the seeds of everything. Tiny differences in density that, over billions of years, would grow into stars, galaxies, and eventually you, sitting here listening to a video about the universe in your favorite pajamas. Those slight variations are clues. They tell us how matter was distributed in the early universe. They reveal the physics of the cosmos at its birth, and they let us test theories about how space and time unfolded in the first few heartbeats of creation. Even the shape of the universe leaves its fingerprints on the CMB. If space were curved like a sphere, or saddle-shaped, or flat as a pancake, those geometries would subtly distort the way light travels through space. By measuring the size and distribution of the fluctuations in the CMB, scientists can infer the large-scale structure of space itself. And so far, all signs point to a universe that is flat, at least within the limits of what we can observe. It's a bit like looking at the pattern of waves on a pond to figure out the shape of the shoreline. The way those ripples stretch and move carries information about the environment they travel through. In the same way, the CMB carries encoded messages about the shape, size, and ingredients of the universe. It's light as data, photons as historians, and there's something deeply soothing about imagining that glow. A soft, gentle wash of ancient light, not blinding or fiery, but calm and even. Not one that you can see with your eyes, but one that's always present. It's like the universe's own lullaby, still playing after all these years. If you could tune in with the right kind of radio, you'd hear it everywhere. Not as a song, but as a faint static warmth, a constant low-level presence woven into the very fabric of space. It's the closest thing the universe has to a baby photo, a snapshot of its earliest moment of clarity. And it's still whispering to us, long after the stars were born, long after galaxies spun into shape, long after Earth began its slow dance around the sun. That light has outlived generations of stars, crossed unimaginable distances, and arrived here in your lifetime, ready to tell its story. In a universe filled with mystery, the CMB is something solid, something we can measure, map, and understand. It reminds us that we don't need to chase the edges of space to learn about its beginning. Sometimes the answers are already floating all around us, waiting patiently in the glow. So the next time you look up at the night sky, try to picture it not as black and empty, but filled with an ancient light too faint to see. It's been traveling for over 13 billion years, stretching with every passing moment, carrying the quiet history of everything. And even now, in the stillness of space, it continues to shine. Is there a true edge to the universe? A final frontier, a cosmic curtain, some ultimate boundary where space just stops? It's a question that keeps bubbling up, not just in science fiction, but in real scientific circles, whispered between chalkboards and telescopes. While mainstream cosmology leans toward a universe with no hard edge, some speculative theories and thought experiments nudge open the door to stranger possibilities, places where boundaries might exist, even if we can't quite see or feel them. Let's start gently, with the idea that our three-dimensional universe could be a kind of surface, or brain, floating in a higher dimensional space. This is one of the central ideas in brain cosmology, an offshoot of string theory. In this picture, our universe might be a vast three-dimensional membrane, short for brain, existing within a higher dimensional bulk. We are confined to this brain. All the particles and forces we know, except gravity, are stuck here, like bugs trapped on a soap bubble. Gravity, being a bit more adventurous, might leak into the surrounding dimensions, which is one reason some physicists think it seems so weak compared to the other forces. If this idea is correct, then our universe could have an edge, not in three-dimensional space, but in the higher dimensional bulk we can't perceive directly. You could imagine the brain having a limit or boundary in the dimensions we don't experience. From our point of view, everything seems continuous and edge-free. But from the perspective of a hypothetical five-dimensional being with excellent vision, we might look like a cosmic disk with boundaries at the rim. It's a little unsettling to think of being watched by something with more dimensions than we can comprehend, but comforting too. We'd be the strange mystery to them. Then there's the idea of cosmic domain walls, boundaries between different regions of space where the laws of physics might be slightly different. These walls are predicted by some theories of symmetry breaking in the early universe. Imagine that space went through a phase change, like water freezing into ice, but it didn't freeze the same way everywhere. Some regions froze with one set of rules, while others chose a different path. The borders between these patches could form domain walls, massive structures stretching across space, dividing one cosmic regime from another. In most models, these walls would have quickly disappeared or diluted into irrelevance, but some speculative scenarios imagine they could still exist, lurking in deep space like silent sentinels. Passing through one might be undramatic, or it might be like stepping into a parallel universe with a slightly different version of chemistry. Your atoms might behave just a little bit differently. Your tea might taste slightly more lemony for no apparent reason. Speaking of passing into other realms, some thinkers have wondered whether our entire universe might be the inside of a bubble. Not metaphorically, but literally, a bubble of space that formed during a phase of cosmic inflation. Picture the early universe frothing with quantum fluctuations. In some regions, inflation stops, and a bubble of space forms with its own properties, including the constants of nature, the strength of gravity, the number of spatial dimensions. Each bubble is a universe unto itself. This is sometimes called eternal inflation, and it leads naturally to the idea of a multiverse, a foam of bubbles, each with its own unique physics. In this view, there is a kind of edge, where our bubble universe meets the inflationary background, or where it might one day collide with another bubble. But such collisions would be beyond rare. If we are a bubble in a vast cosmic foam, our neighbours are too far away to ever meet, and the edge of our bubble will be more theoretical than tangible. Still, there's a strange poetry in imagining the universe as part of a fizzing sea of other realities, each expanding into the void like soap on a dish. And then there's Gödel's rotating universe. Yes, that Gödel, the same one who poked holes in mathematics with his incompleteness theorems. In 1949, he came up with a solution to Einstein's equations that describes a universe rotating as a whole. Not individual galaxies spinning in place, but the entire fabric of space-time slowly twisting like a vast cosmic spiral. In this strange model, time and space are curved in such a way that you could, in theory, travel along a specific path and arrive back at an earlier point in time. Essentially, a time loop. Gödel's universe has no edges, but it does blur the line between boundaries of space and boundaries of cause and effect. What's more disorienting? A wall at the end of the universe, or the ability to meet yourself before you were born? Now, before you book your round-trip ticket to yesterday, it's important to note that Gödel's rotating universe doesn't match what we observe. Our universe isn't spinning in that global way, and the kind of time loops he imagined remain theoretical at best. But the model is valuable, not because it's physically realistic, but because it stretches our minds. It reminds us that the rules of the universe are not set by our imaginations, but by equations, and those equations sometimes allow for worlds stranger than fiction. Another wild idea proposes that the universe might be like a hologram, not in the science fiction sense of flickering projections, but in a very precise mathematical way. According to the holographic principle, everything that happens in our three-dimensional space might be encoded on a distant two-dimensional boundary. something like the way a hologram stores a full image in a flat surface. In this case, the true edge of our universe isn't a wall or a border, but a boundary where the fundamental information is stored. We're not talking about simulations or digital trickery here, just a different way of describing the same physics. The idea emerges from string theory and black hole thermodynamics, and it's still speculative, but tantalizing. The deeper message behind all these theories isn't that we'll find a physical wall at the edge of space, or a sign that reads, "End of universe, authorized personnel only." It's that space might have limits and boundaries in ways that don't look like what we're used to. Edges might exist in higher dimensions or in the initial conditions of our universe, or in the information that underlies everything. They might not look like walls. They might look like changes in physics, changes in curvature, changes in the rules themselves. It's entirely possible that we live in a universe with no edge at all. But it's also possible that we're brushing up against ideas that feel like edges, limits of what we can know, of what we can observe, of what our equations can describe. And that's a kind of boundary too, isn't it? We are creatures evolved to live in rooms, on continents surrounded by air and gravity and things that end. So when we step into cosmology, we bring those instincts with us. We search for edges because everything else in life has them. But the universe, as always, is under no obligation to follow our expectations. Maybe the cosmos loops quietly in on itself. Maybe it stretches infinitely in all directions. Maybe it perches delicately on the surface of a higher dimensional bubble. Or maybe, just maybe, it's shaped like something we've never thought of before. Something that curves and connects and folds in ways our minds can barely begin to grasp. And yet, here we are, floating in that mystery, wondering about boundaries while being part of something that might not have any. There's something peaceful in that, don't you think? That the universe could be endless, not just in size, but in possibility. That even the questions themselves might stretch on forever. It's a big enough challenge just trying to understand this universe, with its billions of galaxies, swirling black holes, cosmic background radiation, and space that might curve or stretch forever. We already have plenty to ponder. But every now and then, cosmologists and physicists like to stir the pot and ask an even bigger question. What if this universe isn't the only one? Welcome to the multiverse hypothesis. It's one of the most fascinating, bizarre, and thoroughly speculative ideas in modern physics. It suggests very simply that there might be more than one universe, perhaps many more, maybe even infinitely many. Universes with different physical laws, different particles, different timelines. Universes where cats walk on ceilings, gravity flows sideways, or your high school haircut choices turned out much better. Before we go too far, let's make something clear. There is no direct evidence for the existence of other universes. None. We haven't seen them, measured them, waved to them across a dimensional fence. The multiverse is a framework, not a conclusion. A way of thinking that arises naturally from certain theories, but still lives firmly in the land of speculation. That said, the idea isn't as wild as it might sound. In fact, there are several different versions of the multiverse hypothesis, each with its own flavor of cosmic imagination. The first and most intuitive is called the cosmic multiverse or bubble universe model. This idea comes from inflation theory, the rapid expansion that occurred just after the Big Bang. According to this view, inflation didn't happen uniformly. Instead, it could have created many separate bubbles, each forming its own universe, expanding and evolving independently. Each bubble might have its own laws of physics. Some could be too strange to support matter. Others might have entirely different kinds of particles, forces, or even dimensions. We happen to live in one of the lucky ones where the conditions are just right for stars, planets, and long-winded late-night podcasts. In this bubble model, our universe is like a single soap bubble, floating in a cosmic foam. Other bubbles might exist, endlessly drifting, forever separate from ours. If you're imagining a cosmic sink full of dish suds, you're not far off. Then there's the quantum multiverse, which comes from interpretations of quantum mechanics, specifically the many worlds interpretation. This version says that every time a quantum event has multiple possible outcomes, all of them actually happen in separate branching universes. So in one universe, you hit snooze this morning and stayed in bed. In another, you got up early and made pancakes. In yet another, you tried to make pancakes, but accidentally discovered teleportation instead. Each branch is a new version of reality, created by the unfolding of every possible choice and chance. This isn't just a thought experiment, it's a serious interpretation of quantum mechanics developed to avoid the awkwardness of wave function collapse. But like the bubble universe idea, it's not something we can currently test or observe. We can't jump between these branches. There's no interdimensional train station with a mustachioed conductor offering trips to the universe where you became a world-famous harmonica player. And yes, in at least one of those infinite branches, you probably have a mustache, even if you've never grown one. Statistically speaking, it's almost guaranteed. Somewhere out there, you might be giving a TED talk about alternate facial hair choices and their impact on parallel timelines. There's also the mathematical multiverse proposed by cosmologist Max Tegmark. This is the idea that all mathematically consistent structures exist as physical realities. In other words, if it's mathematically possible, it exists somewhere. That includes not just other universes with different particles, but ones with entirely different logical rules. Universes where the value of pi is different or time flows in a spiral. It's a bold suggestion, almost mystical in scope, and probably impossible to test. But it's compelling to think that math itself could be the fabric of existence, spawning every possible variation of reality like an infinite library of cosmic blueprints. These multiverse ideas, while intriguing, do face criticism, and rightly so. One of the biggest issues is falsifiability. If other universes are forever inaccessible, how do we study them? How do we know they exist at all? Science works best when we can test predictions, measure results, and refine our models. When we're talking about realms that can't be reached by any signal, it's hard to apply the usual scientific tools. Some physicists see the multiverse as a warning sign, a symptom of theories stretching beyond their useful limits. Others argue that the multiverse helps explain why our universe has the properties it does. If there are countless universes, each with different constants and laws, it's not surprising that we happen to live in one where life is possible. It's a cosmic version of survivorship bias. We exist here because here is a place where existence is possible. It's a bit like rolling dice in a casino with an infinite number of tables. Most tables produce nothing interesting, but at one of them, by pure chance, the dice land just right. That's the table we're sitting at. We didn't cheat, we didn't rig the game, we just happened to be in the room where the numbers worked out. Some cosmological models even suggest that multiverses might be indirectly detectable, perhaps through unusual patterns in the cosmic microwave background, caused by collisions between bubble universes. So far, nothing has shown up, but physicists are keeping an open mind. After all, some of the most incredible discoveries in science started out as strange ideas waiting for the right tools. Whether or not other universes exist, pondering them stretches our imaginations. It encourages us to think beyond the limits of what we can see. It reminds us that reality might be far broader, stranger, and more playful than we ever expected. It invites us to be humble in the face of what we don't know, and bold in exploring what we might someday learn. And really, isn't that what science is all about? Not just answering questions, but discovering bigger ones. Not just building knowledge, but expanding wonder. Even if we never find another universe, even if this one is all there is, we've already proven that human curiosity can reach across galaxies, through time, and into ideas as vast as the multiverse itself. That's no small thing. So whether you believe in a single cosmos or an infinite stack of them, whether you prefer one timeline or a branching forest of quantum possibilities, remember, somewhere in the multiverse you're doing something brilliant, or unusual, or inexplicably involving a llama. And in this universe you're here, thinking about space, sipping tea, and quietly wondering what else might be out there, just beyond the veil of what we know. That, in itself, is a kind of cosmic magic. Where does space stop? It's the question that brought us here, whispered softly at the beginning like a child asking if the sky has an end. And after wandering through galaxies, curved dimensions, cosmic microwave whispers, and the edges that may or may not exist, we find ourselves gently circling back to where we began, still wondering. We've learned that space doesn't behave like a room or a box or a stretch of road. It doesn't come with a fence or a finish line. It doesn't need walls to be complete. It can be infinite or finite and unbounded. It can stretch, loop, curve, and fold in ways our minds are only beginning to understand. It can even carry galaxies away from us faster than light, not because they're moving, but because the space between us is growing. We know that there is a limit to what we can observe, a cosmic horizon beyond which light has not yet reached us. But we don't know what lies beyond it. Maybe the universe keeps going forever, or maybe it folds back on itself in a gentle arc we'll never see. Perhaps our universe is one bubble among many, drifting in a higher dimensional sea. Or perhaps the multiverse is just a poetic idea, beautiful but unreachable. What we do know is that space is not empty. It's alive with structure and subtle energy. It stretches with time. It carries the light of ancient stars and the hum of the Big Bang. It has no center, and as far as we can tell, no end. And still questions remain. Is the universe infinite, or just very large? Is it curved, flat, or something else entirely? Is it one of many, or all there is? And if there were an edge to space, what would be on the other side? We may never find all the answers, but that's not a failure. It's the heartbeat of science. The beauty of the cosmos isn't just in what we know, it's in what we don't. It's in the quiet courage of looking up and asking anyway. The search continues, as it always has, through telescopes and equations, through gentle dreams and midnight thoughts. Every photon we catch, every map we make, every model we refine brings us a little closer, even if the destination keeps shifting like the stars. Maybe that's the whole point. Maybe space never stops, not because it's infinite in size, but because it's infinite in mystery. Maybe it doesn't have to end for it to matter. Maybe it just is, sprawling quietly in all directions, an invitation, not a boundary. In the introduction, I asked you a few things: where you were listening from, what time it was, and whether the question, where does space stop, might keep you awake or lull you to sleep. I hope by now you feel more relaxed. I hope your thoughts have softened into that quiet space where wonder lives. And if you're still awake, just barely, I hope you found some peace in the asking, even if the answer remains elusive. Because really, that's what space gives us. Not just stars or silence, but the freedom to ask the biggest questions of all. And perhaps space never stops because questions never do.